Welcome to section 9.3, more about parabolas and their applications. Okay, so note we are only covering objective 2 and 4. So, the exponential function, what is it? Well, basically, if we have some number, we're just going to call it a, where a is greater than 0 and a is not equal to 1, these are very important, and all real numbers, x, what do we have? Well, we have this function, f of x. Once again, f of x means it is a function. When you see that notation, we know it's a function. Equals a to the x. And this is the exponential function. So let's go ahead and play around with some of these. Let's graph two different looking ones where their bases are different. So notice these are exponential. How do we know? The variable is in the exponent. Once again, that's how you know if it's an exponential function. Okay, so this is the main difference. So now what do we have? We have two functions. One where the base is 4 and one where the base is a half. And we're told to graph them. So basically, the concept is you need to graph at least 3 points. And any intercepts if you can. So let's go ahead and set up a table of values. We want at least 3 points and we want to try to find the intercepts. So first off, should we be picking values for x or y? Well, it's easier to pick values for x because this is in function notation. So let's go ahead and do that. If I pick 0 for x, that means I have 4 to the 0 power, right? And anything to the 0 power is just 1. So I have the point, and let me just go ahead and write this out in the coordinate notation. That's going to be 0, 1. Okay, let's go ahead and write that down. And I'm going to graph that in blue, 0, 1. Okay, so that is my y-intercept. Sorry, not my x-intercept, because x is 0. Next one, what's another value we can think of? Now, I always like to pick positive values and then some negative values. So let's first go with a positive. How about 1? Well, that means we get 4 to the first power, which is just going to be 4. So that's the point 0, 4. I'm sorry, 1, 4, not 0, 4. 1 and then up 4, 1, 4. And we need at least one more point for graphing. So let's go ahead and pick a negative. As always, I always pick positive, negative, and then 0 if I can. Negative 1, so that's going to be 4 to the negative 1 power. And what do we do with negative exponents? Well, we take the reciprocal. So that's a fourth, which is going to be 0.25. So that one's kind of hard to graph. Once again, we're just going to give an estimate. So negative 1 about there. Negative 1, and I'll do a fourth. Always give the exact value when you write the number. Okay, so let's see. Can we find a y or an x-intercept for this? Well, for an x-intercept, I'm going to go ahead. How do I solve an x-intercept? I need to set y to 0, right? So that means, let's go ahead and do this on the side here, and I'm just going to show you why we're not going to have one. So f of x equals 4 to the x. And we're trying to find if we have any x-intercepts. Running over those words today. Okay, so we're trying to find if we have any x-intercepts. So we're going to set y to 0, and then we're going to solve. Now, just looking at this, let's ask ourselves, do we know of any number I can raise 4 to that will give me 0? Well, you could say, what about 4 to the 0 power? But remember, anything to the 0 power is 1. And then any positive power that 4 can be raised to is going to give me an actual number bigger than 0, right? And then any number I raise 4 to that's a negative number, that's just going to give me a reciprocal number. It's not possible to raise 4 to a number and end up with 0. So this does not exist. DNE for shorthand, we don't have an x-intercept. And this is actually going to be true for pretty much all exponential functions when they're in this basic main format of a to the x. Okay, so the x-intercept does not exist. So we're going to write DNE. Okay, just waiting on my pen here. All right, DNE. Okay, let's go ahead and graph this in. We have our 4 points. We showed the work for trying to find that, and then here we go. So what does it mean when it does not exist? Well, basically, for an exponential function, they grow bigger and bigger and bigger, and they get closer and closer to the x-axis, but it doesn't actually touch it. And so what this has is an asymptote. Right down along here, I'm not going to be able to fully dot it in, so I extend it to the sides. We have an asymptote at what? Well, at y equals 0. Okay, so that's always for the basic form of a to the x power for an exponential function. When things start getting more fancy, which they don't do in the courses 82 and 103, they get fancier in Math 135. So they get to see something a little more fancy then. So that was the first one. Not too bad. Let's go ahead and take a look at the next one we have, which is f of x equals half to the x power. Now this is weird. It's a fraction. But let's just go ahead. Once again, we need at least 3 points for graphing. And then we need to check for our intercepts. So if I pick 0, which I always do if I can, I'm going to have a half to the 0 power. Well, anything to the 0 power, remember, is just 1. So that's going to be the point 0, 1. And I'll graph this in green. So 0, 1. Now the next one, we have, let's see what else we can pick. As usual, I always said a positive and then a negative. It's just a good rule of thumb. Let's see, so negative 1, let's do that this time. So we have a half to the negative 1 power equals, oh, what do we do with a negative exponent? Once again, we take the reciprocal, right? So that's just going to be 2 over 1, which is just 2. So we have the point negative 1, 2. Negative 1, and then up 2, negative 1, 2. And one more point, and then we'll try to find our intercept. Let's see. Let's go positive 1. Why not? Half, and then that's going to be to the positive 1 power, which is just going to be a half. So that's going to be, what did I say, 1/2? Right there, 1 1/2. Now, if you wanted to be sneaky, or if you just were interested in finding a bigger number, let's try maybe negative 3, right? Well, that'd be a half to negative 3rd power, which means we're going to take the reciprocal of a half to get rid of that negative. So that'll be 2 to the positive 3rd power. We got rid of that reciprocal. And then 2 to the 3rd power is 8. So the point negative 3, 8 is also on our graph. So negative 3 and then up to 8, 5, 6, 7, 8. Right there, negative 3, 8. That's also on my graph. We didn't need 4 points, but once again, just showing you the different points you can find. And then the same thing here is going to happen if you try and find your x-intercept. It does not exist. So our x-intercept does not exist. And then this would be our y-intercept. And for exponential functions, unless I ask you to specifically state the intercepts, I usually don't ask for them, unless I'm stating them in the problem that I would like you to find them. If you're just told to sketch a graph, just required to have 3 points and your asymptote. And, once again, for the green graph, you also have the same asymptote, which I can't really redraw again, but the same asymptote exists for the green graph. And then let's go ahead and draw in the green graph. It approaches the horizontal asymptote, but it does not touch it. It's right above it. And then our arrowheads on both sides. Let's go ahead and label our graphs. F of x equals 1/2 to the x power, and then f of x equals 4 to the x power. All right, let's see what else we have. Characteristics of the graph of f of x equals a to the x. So there are 4 characteristics. First one, the graph contains the point, contains 0, 1, which is the y-intercept. Okay, so that's always going to be the y-intercept, and that always is going to be on that graph of the form a to the x power, which, if you'll notice, they both shared that same point. Now the other characteristic is 1 to 1. So for each x input value, you have 1 y input value. And when a is greater than 1, the graph rises from left to right, like this. And when a is less than 1, it rises in the other direction, that way, which we can once again see in the examples here. When x was greater than 1, when we had 4, our graph went up. And when x was less than 1, we had a half, it went down. Once again, reading from left to right, like you'd read a book. Now, what other things do we know? Well, the graph approaches the x-axis but never touches that, which we'd noticed. So there is a horizontal asymptote at y equals 0, the x-axis, which once again we saw when we graphed right here. And the last bit of information to know about this is the domain. The domain is from negative infinity to positive infinity, and the range is 0 to infinity, and not including 0. Why do we not include 0? Well, once again, remember, we have the horizontal asymptote at y equals 0, where our graph cannot touch it. So all of these values, not including 0 and up, are our range, and our domain are all possible values from left to right, so positive infinity and negative infinity. Now, properties for solving an exponential equation. What are the properties? Well, for a greater than 0, and when a is not equal to 1, if we have a to the x equals a to the y, then what can we do? Well, then it must make sense if the bases are the exact same thing, and they're equal to each other, then x must be the same thing as y. Then x must equal y, so we can just equate the exponents. Okay, so this is what comes in handy when you're trying to solve exponential equations. If you can find a way to make the bases the same, then you just set the exponents equal to each other. So steps for solving an exponential equation. What's the first thing? So first thing, need to have the same base. So same base on each side. Side of what? On each side of the equal sign. So same base. So in this case we had a and a. What's the next step? Step 2. Simplify the exponents. Step 3. Set the exponents equal or equate the exponents. And step 4, solve. We don't need to worry about checking exponential equation answers. And this is on page 662 if you want to look at that a little more. There's a little more detail in the book on that. Okay, so let's take a look at an example for solving. So, what kind of an equation is this? Before we do anything, we need to determine what kind it is. It's exponential. How do I know that? Well, the variable is in the exponent. So it's not quadratic, like when we have x squared. That's quadratic, because the highest exponent we see is a square. And it's not linear, because linear would have x to the first power. This has the variable in the exponent, which is different. We haven't seen that before now. So we know it's exponential. So the plan for this is to have the same base on each side. And currently we have 0 on one side and 3x minus 12 on the other side. So I need to think about this. So real quick, sorry, these numbers are not the right numbers. It's the same concept though. This should be 8x minus 16. 8x minus 16. So it's exponential. How do we know? Well, because there is a variable in the exponent, but it's not set up correctly. So what I'm going to try to do is I'm going to get the item that has the variable in the exponent. I'm going to get this one by itself and move everything else to the other side. So I'm working towards getting it so that we have one side equal to another. So now the next question is, I have a base to an exponent, but I don't have a base to an exponent on this side. And then the other question is can we create the same base from both of these? So I'm going to think. I'm going to play around with 8 and play around with 16. 8 is 2 times 2 times 2, right? So 8 is 2 cubed, because there are 3 2's. So 8 would be 2 to the third power, and we still have the x equal to. Now what is 16? 16 is 2 times 8, and then 8 is 2 times 2 times 2, which we already saw. So 16 is the same as 2 to the fourth power. So let's rewrite 16 as 2 to the fourth. Hey, do you see what we just figured out? I now have the same base. They're both 2's. That was my goal. So I have 2 to the 3x equals 2 to the 4. So since the bases are the same, what can we assume? Since they're the same, we can assume that 3x must equal 4. So now we can equate the exponents and solve for x. So x equals 4 over 3. And we're done. So the main thing, the trickiest part, is being able to find a way to make these match. And that usually means you gotta fiddle around a bit with the bases. Play with them, factor them, just find different ways to factor them. It's usually the best bet. So let's take a look at the next one, example 3. Okay, well this time we have two items equal to each other already. And is this exponential? It is, because I have my variable in the exponent. So now my goal is, can I find a way to match 4 and 16? Well, let's see. So 4 is just 2 times 2. 16 is 4 times... Hey, it's 4 times 4. So you know what? Instead of breaking down 4, let's stick with 4 as the base. We could go down to 2's, but why not? Let's stick to 4 as the base. So then it's 4 times 3x minus 1, not times, to the 3x minus 1 power. And 16 is 4 times 4, so that's going to be 4 squared to the x plus 2 power. Once again, we're just rewriting 16 as 4 to the second power. Okay, let me rewrite this again. Using the rules of exponents, that's going to be 2 times x plus 2 in the top. Hey, and now the bases are the same. So since the bases are the same, what can we do? What can we assume? We can assume that these must be equal to each other. So let's go ahead and write those down equal to each other. 3x minus 1 equals 2 times x plus 2. And let's go ahead and solve. This looks like a linear equation we know how to solve. Okay, solving linear, let's go ahead and move the 2x to the other side. Add the 1 to both sides. And we get x equals 5. And we're done. So you could check your answer if you wanted to for fun. You're not required to check them for the exponential, because there's no harm in raising any number to any power. Nothing can go wrong in that way. So for fun, let's give it a check. So it's just going to be 4 times 3 to something minus 1 equals 16 something plus 2. And we found out x should 5. Okay, so we have 4 to the 15 minus 1 should be equal to 16 to the 5, 6, 7. So 4 to the 14 should be equal to 16 to the 7. And let's type that into the calculator. Okay, so 4 to the 14th is 2, 6, 8, 4, 3, 5, 4, 5, 6. And 16 to the 7th is 2, 6, 8, 4, 3, 5, 4, 5, 6. Once again, you don't need to check for exponential problems. I'm just showing you that it works out. All right, the answer checks out. If you want to check it, once again, if you have time at the end of the exam, not much rushing you, it's a great time to just check your answers. If you just want to make sure you're right. Okay, let's move on. Example 4. This is, the last one for this section. Now, this one looks interesting. What is weird about this one? Well, I mean, the variable is in the exponent, so that's not that weird. We've seen that before. So it's an exponential equation. But my goal is to match the bases, and right now, those bases look kind of weird. But as usual, I'm trying to think of what numbers they have in common. Now I know 3, it doesn't have anything in common with 16, but 3 has something in common with 9. And 4 has something in common with 16. Man, if only I could find a way to flip the 9 and the 16, then they'd kind of be in line with each other. You know what? Do we know a way to flip fractions? We do, and it happens to do with exponents. I'm going to use the reciprocal rule. So 16 over 9 is the same as 9 over 16 to the negative 1 power. Look at me being all sneaky with the exponential rules. Okay, so now I have the 4 and the 16, which have the similar thing, and the 3 and the 9, which have a similar thing. They're lined up together. That's good. Let's see. Hey, 9 is 3 squared, and 16 is 4 squared. So you know what? Three over 4 squared is 9 over 16. So let's go ahead and do that. Let's rewrite. Wait, real quick, let me write this down. Let's rewrite 9 over 16 as 3 over 4 squared, and that is still to the negative 1 power. And then using the power to power rule, multiply those two together. We have 3 over 4x equals 3 over 4 to the negative 2 power. So, awesomeness, now we have the bases are the same, so what can we do? We can equate the exponents. And x equals negative 2. Okay, so the main thing with these problems is just taking a look at the bases and think of the factors. So factors of 9 are 3 times 3. Factors of 16 are 4 times 4. And then try to look at the two and figure out how they're related. And then play around with exponents to make them look the same. So that's kind of where the trick is being able to play with exponents. Alright, if you have any questions or need any help with the lecture notes or the homework, please send me an email or stop by an office hour.